Okay, so off we go, picking up with where we left off. So we were talking about vector surface integrals. Remember, the big idea of vector surface integrals is our primary interpretation is that they compute flux. And our primary interpretation of flux is that when the vector field represents fluid flow, flux tells us quantity of fluid per unit time. And that's the big idea. Okay, so various things to say about it. Now, the next thing to talk about is coordinate surface integrals, and arguably these are a new kind of integral. Also, arguably, they're a different notation for what we just talked about, namely vector surface integrals. So this is going to come out of this formula that we wrote down for the ds vector. And let me just remind you that quite a while ago, when we first computed that capital N vector, we pointed out that it was this cross product, which we can expand in coordinates. Nothing really happens when you do that. And then you can crank out the cross product. Again, we're not really doing anything there specifically. This is just a different way to write that cross product, just to kind of multiply it out. And again, we noted this sort of weird seeming coincidental thing that looks like a two-dimensional change of variables stretching factor, which isn't geometrically what we're interested in here, right? So a little surprising that showed up. But anyway, having made that observation and then kind of distributing, you can take this product, kind of distribute the ds dt, and with this, again, interpreted as a two-dimensional change of variables stretching factor, you can kind of cancel those. Again, a little math crime. This is not a fraction. There is no cancellation. But the reason that we like this notation is that the nonsensical cancellation actually always leads you in the right direction. Right? And so, as it turns out, I'll say it this way, a reasonable interpretation of what this ought to be is that it should be dx dy. And again, now there's a really good geometric interpretation of this as well. If you'd like to have a geometric take on why should I think of the third coordinate of my ds vector as representing an area in the xy plane, how is that natural? Come to office hours. I'll be very happy to show you. There's a very natural point of view on that, but not something that we're going to talk about in class. You don't need to know it. It's just interesting. Okay, with all of that done, again, it's just a matter of kind of rewriting things. What we have is a different way to represent the ds vector. You can represent the ds vector as a vector of differentials like this. And applying that idea, plugging in ds is this, remembering that our vector field has coordinates. Very often we write PQR. You can crank out this dot product like so. Again, I didn't really do anything. I'm just kind of moving things around on the page. And what we get then is our alternate notation for how to represent flux. This vector surface integral you can instead represent like this. Now, you remember we did something totally analogous to this back when we were talking about vector line integrals. We had coordinate line integrals. And you can interpret those as an alternative notation for vector line integrals, right? And doesn't seem to bias very much. Certainly in this case, it looks like it's just a bulky, unnatural, non-intuitive take on vector surface integral. And given what I've shown you, I'd have to agree with that. Yeah, absolutely. So that said, all of the same sort of comments come with this notation as came with coordinate line integrals. Namely, this is a special case of some really heavy stuff. There are excellent, powerful reasons to want to do this. We're not going to see them in this course. right? This is high. This is a significantly higher level ideas that wouldn't be appropriate in 219. But that's why this notation persists, is because it's representative of really good ideas that have later applications. And because of that, it's in common use. So you are going to see this, even if you're not a math major, even if you go into engineering. Again, I saw this kind of stuff in physics classes, here and there. Maybe not a huge amount, but definitely here or there. And so you need to know what to do with it when you see it. And when you see this, my suggestion is to recall that, let me squeeze this down a little bit more. When you see this notation, remember that these differentials are just an alternative notation for the ds vector, right? And so the apparent, seeming integrands here, the integrands that they're being multiplied by are just the vector field for your vector surface interval. Does that make sense? So all you got to do is remember which order these little product differentials get written down in. And so dy dz, dz dx, dx dy, not that hard to remember. And you can interpret correspondingly. Okay. All right. Let's see here. More things that need to get said. Symmetry theorems. We talked about symmetry theorems a lot. You can probably anticipate everything that I'm going to say about scalar surface integral odd symmetry theorem. It's just like all of our other odd symmetry theorems. If you have an odd integrand and a symmetric domain, wrong color, sorry. Specifically, you have both of these conditions satisfied using the same plane for both kinds of symmetries, then your integral is equal to 0. You don't have to slice up, parameterize, all the usual stuff, antiderivatives, plugging in, tedious computate. You don't have to do any of that, right? Just show the usual 5 conditions, right? 5 sort of checkpoints of what we want to see for a complete symmetry argument. Declare victory, integral 0. So, really, really nice. And as, again, you might expect, based on what we did with line integrals, this is scalar only. Scalar surface integrals only. If you try to apply this to vector surface integrals, it does not work. It doesn't work. There is no such theorem. There is no odd symmetry theorem for vector surface integrals. Roughly speaking, the reason why is if you look at your symmetric domain, now here's my attempt to draw a surface that is symmetric through this plane that I've got drawn here, just an arbitrary symmetric surface. And we're interested in computing a vector surface integral, right? Vector surface integral, which of course we could write like this just as well. And let's think about how the normal vector shows up in this picture. And you can see a couple of unit normal vectors like here in light blue. And they're not the same. And the areas, these little areas are the same, right? These normal vectors are not the same. And not only that, it's not just that they're not the same, they're also not negatives of each other either. There's just no good news there concerning those vectors. So odd symmetry theorem doesn't work. Be very, very careful about that, please. If you forget this ugly little reality and try to make an odd symmetry argument for a vector surface integral, it's all nonsense and easy landmine to step on. So be careful. Okay, pausing for questions. Everybody okay? All right, moving along. Okay, Yeah, so there's some neat analogies to be noticed between line integrals and surface integrals. I've commented on some of those as we've developed them. I won't repeat those little quick observations, but here I want to show you even more strength of analogy and tell you, roughly speaking, why these analogies, these seeming coincidences, come up. It's because line integrals and surface integrals are ultimately the same thing. They're both integrals of differential forms. Now, what's a differential form? Well, again, not something we're going to talk about in this class. The point to this observation is not exactly what is it they have in common, but that they are special cases of the same thing, and therefore that, well, of course they have common features. They are literally the same idea, just applied in a different context. So anyway, heads up about that. And again, nice little cultural point to know that it's not a coincidence, to know that there is this common shared sort of unification of these ideas. And the result of those analogies, the result of that those common features is what I'm about to show you here. This is a bunch of stuff we've already done. Nothing new on the screen to speak of. I'm going to now color code much of what's on the screen and show that the objects playing certain roles in these two different stories, the objects playing analogous roles in the pictures also play analogous roles in the equations, and the consistency of the analogy is shocking. It's basically perfect. So here we go. We've got parameterizations on both sides. Parameterize the curve, parameterize the surface. You can talk about derivatives of the parameterization. The derivative of a parametric curve, of course, gives you velocity, which participates in those equations that we recognize from long ago, right there and there. And then there's, let's see, I'm going to call a derivative of the surface parameterization. Now, it's not really quite a derivative, but it's a cross product of derivatives. It comes immediately out of honest-to-God derivatives. So I'm going to call it a derivative. A little bit of a stretch, right? But that n, notice it shows up in exactly analogous places in the surface integral formulas as v did in the line integral formulas. Okay, we can talk about the unit vector pointing in that direction, unit tangent vector, unit normal vector. Those show up in analogous ways in those equations. We can talk about the size of the corresponding piece of the domain, right? We've got a little piece of curve there of size ds. We've got a little piece of surface here of size d capital S. Again, the analogy continues. Perfect, right? Everything falls into place. We can talk about the vector differential dx vector over here, telling us, of course, reminder, the dx vector, the direction is the direction of the orientation. The magnitude is equal to the size. That vector, its analog over here is the ds vector. Again, the direction tells you the orientation. The magnitude tells you the size, in this case area, of the little piece of surface. And notice it shows up analogously in these equations. I mean, it's a real eyebrow raiser. Look how strong that analogy is. I think the colors make it really pop. How, oh my gosh, we're doing the same thing in both contexts. Geometrically different, of course. Geometrically a different context, so different details, right? But the relationships are extremely powerful. Does everybody see what I mean there? Any questions about any of that? Likewise, if you continue looking at the equations, how you write down vector line integrals, how you write down surface integrals, and you can go through and color code again, and the color coding will again make perfect analogies and how these players participate in the various equations. It's all the same basic analogous roles. Okay, so I like pointing that out. I think that's helpful in two ways. Again, as y'all have heard me say before, I think it's good for y'all to know certain little cultural points, to know that there are, even if you don't know the higher ideas, to know that there are reasons why things that we can observe at this level happen. I think it's a good thing to know, right? But also, when you see that there are strong analogies like this, you can take whatever you understand from one story and use that to kind of help you make sense out of and come to understand what's going on in the other story. I think it's a good learning tool as well. Yeah.
Can you briefly go through again how you got from TDS to VDT?
Oh, yeah. So that's we first did this back in chapter 3, and the big idea is, let's see here. Yeah. If you take this formula for ds and plug that in here, let's see here. Then, roughly speaking, when you plug that in, this is what's going to come out. And there's a little couple of dots to connect there. But if you look back to chapter 3, you'll see the details for that. Yeah, absolutely. Yeah. Okay, let's see here. Let me zoom back out. There we go. Okay, all right. So, yeah, I just wanted to point that out. I think it's a nice little sort of observation, nice little thing to be aware of, and I hope y'all will find that useful. Okay, moving along. So 7.3, this is our last big section. It's going to take us most of the rest of the semester to finish section 7.3. It's an enormous section. It's another one of these 3, maybe 4, maybe 5 day sections. There's a tremendous amount of stuff to cover. Really ought to be at least 2 sections, arguably 3, depending on preferences. Anyway, so the author of our textbook starts off by talking about Stokes' theorem. It's a reasonable point of view. I take a different point of view. I think it's better to start with Gauss's theorem. I think it's a little easier sort of first step in three-dimensional vector calculus. So we're going to start with Gauss's theorem. And I am going to start by giving you another convention, another arbitrary but standard convention on how boundaries work. This is totally arbitrary, but when you have a three-dimensional solid region, so for example, this solid right here, so this is like a big lump. Imagine a big lump of Play-Doh, but there's an air bubble inside of it. Right? So it's a solid, but it's got a hole in the middle of it. Let's talk about its boundary. The boundary surface is kind of exactly what you think. The boundary is sort of the border between where the set is and where the set isn't. Right? Now, of course, there's boundary on the inside as well. Right? Because, again, that's border between where the set is and where the set isn't. Right? So there's sort of the outside boundary and then the inside boundary. Again, the word boundary is a loaded word. For all of chapter 6 and 7, when you hear the word boundary, knee-jerk reaction, you should think, uh-oh, that's an oriented thing. It's oriented according to a very specific convention. Again, arbitrary but standard. And you've got to think through, right? It is implicit in the use of the word boundary. It is implicit that there is a given orientation, and it's your responsibility as the student to think through and correctly identify what that orientation is. And the rule is as follows. The orientation is always away from the solid. So for example, you take a point like this on the outside part of the boundary, that, what you might call outward, is away from the solid, in the sense that the other way would have been toward the solid. This is toward where the solid isn't, right? This is toward the air, toward the not solid. So away from the solid. Is everybody good on the, okay. Now, a very common mistake, please don't step on this landmine. Very common mistake is to look at this and say, okay, so outward, right? So it's always outward, right? And you remember when we were talking about Green's theorem long ago, and the oversimplified story there was, well, it's always counterclockwise, right? Isn't it just always counterclockwise? And not really, right? That you got to worry about the, depending on the where in the surface, it might technically not be counterclockwise, right? But it always, the region's always on your left, right? That was the convention. Same thing here. It is not always outward. If you're looking at an interior piece of the boundary surface, notice that away from the solid, at this point, the solid is here. Away from the solid is actually inward, not outward. So you got to be super careful about that. Please don't oversimplify too much with that convention. Everybody good? Yeah.
So we're changing our definition of the boundary again? Or?
No, this is what the convention is in this brand new circumstance that we haven't previously addressed. Right? So when we're talking about Green's theorem, that's for solid regions in a two-dimensional plane.
Oh, I see.
Right? And so the boundary is a curve, and there's the convention that's geometrically unique to that circumstance, right? And so this is a different this is now a three-dimensional solid, so we have a totally different convention. Yeah, totally. Okay, so with that settled, I'm going to show you all a new accumulating quantity, which, wait a minute, accumulating quantity, we've proved a bunch of stuff. We've developed a bunch of ideas about accumulating. As soon as you know you have an accumulating quantity, you know that you can think of that as distributed over the interior. We know that there is an associated density because it's just stuff per unit size, and you can always integrate densities. You always get an integral theorem for any accumulating quantity. And I'm about to show you another brand new accumulating quantity, and here it is. Boundary flux. Now, we actually, I guess, kind of saw a version of this back in Chapter 6. You may recall there was the variation of Green's theorem called the two-dimensional divergence theorem, right? And we made the observation that, well, it could be thought of as a statement about two-dimensional boundary flux. And three-dimensional now, the same thing works. Boundary flux is an accumulating quantity. And basically, this is the picture. I'm going to walk you through the idea of what's going on with this picture. When I say it accumulates, what I mean is it accumulates over volumes in the sense that if you have a whole volume, and if you split up that volume then into a one piece of volume and another piece of volume, right, then the whole is the sum of the parts. So when we say accumulates over volumes, what that means is that when you break it up by volume, then that object, boundary flux, will have this feature of accumulation. The whole is the sum of the parts. Okay, so let's play the game here, and let's look at the left piece. On that left piece, outward oriented, of course, boundary flux. Looks like that for the left piece. Outward oriented boundary flux for the right. Color blue. For the right piece, outward oriented boundary flux is like that. When I look at the sum of these boundary fluxes for the parts, right? The sums of these different boundary fluxes. Think about what's happening on this shared face. Well, on that shared face, we're actually going to be computing that flux twice, once oriented in the green direction, once oriented in the blue direction, and of course, those have opposite orientations, and therefore those fluxes are negatives of each other, and therefore they cancel, right? And I go quickly through that because, as I'm sure you've noticed, this is morally equivalent to what we've seen several times previously, right? It's the same sort of appears twice, opposite orientations, they cancel. It's all kind of morally the same argument. So those disappear, and notice that what remains is, as it should be, the outward-oriented boundary flux of the whole. So the whole is the sum of the parts. We have an accumulating quantity, and we basically, therefore, already have a new theorem. Boundary flux, being an accumulating quantity, can be thought of as stuff distributed through the interior. You don't have to think of it that way, but you may think of it that way, and I suggest that we do. Stuff always has an associated density. You can talk about stuff per unit size, right? Now, to be careful, when I say stuff per unit size, my stuff is boundary flux, and so I've got to imagine for some little region, and I've drawn this two-dimensionally because it's just easier to draw, but the stuff for a little region is outward-oriented boundary flux. Density means stuff per unit volume. And that is what I mean by the associated density. Flux per unit volume, and pretty naturally, of course, we call that flux density. Which, by the way, has a formula and alternate name, divergence, and alternate notations depending on your preference, right? Various different names and notations. But ultimately, one thing to keep in mind when you're talking about divergence, when you're talking about flux density, when you see this formula, however, whatever way this might show up, the big thing, in my opinion, that I think you need to make sure you know about this is this. It's flux density. Flux is an accumulating quantity. It's a kind of a stuff, and divergence means how much of that stuff is there per unit volume. Is that cool? Okay. And of course, when you have a stuff and you have the associated density, I'll come back to this in just a second, you can integrate to get an integral theorem, and so that gives us a final result. So we started by looking at boundary flux. We made the observation that it accumulates. The whole is the sum of the parts. And when you have something that accumulates, stuff is stuff per unit size times size. And this is going to be our big theorem then. This is Gauss's divergence theorem. He's sometimes called the three-dimensional divergence theorem, sometimes just the divergence theorem. And it just says if you're interested in computing an outward-oriented boundary flux, you can do so by a triple integral over the interior of the divergence of that vector field. And again, this is a template theorem, right? As soon as you know we have an accumulating quantity, that makes it a stuff distributed through the interior with an associated density, and quantity is an integral of density. So that's where the theorem comes from. What do you think? Okay. All right, let me real quick go back over the stuff that I just skipped. This is actually a really nice opportunity to make sense out of divergence and how to think about divergence. And I'll remind you that we thought about divergence back in Chapter 3, and I made this apology. I can't give you any sense for why, in that context. But I made a claim that divergence represents the amount that kind of the amount that a field is kind of spreading out. That there's an outward, flow away from a given point, and you can kind of see that happening now because divergence. Let me clean up the mess. Divergence being flux. Being flux density, being this right here, right, is telling you per unit volume, of course, right? There you got to deal with the fact that when there's more volume, of course, there's more stuff. Yeah, obviously, right? But per unit volume, it's just telling you the extent to which you have outward flow through the boundary, right? That's what flux is. Flux represents volume per unit time or quantity per unit time, appropriate to the how you've set things up and what kind of units you've got, etc. Flux is telling you outward flow, right? And so divergence is just per unit volume, literally telling you how much outward flow there is away from that point. So this is a justification. This is sort of an intuition for why this claim that I made back in chapter 3. Why does that make sense? Where did that come from? Arguably, this is kind of where it comes from. Now, I'm going to remind you that back in I hit the wrong button. Sorry. Back in chapter 6. Yes, back in chapter 6, we revisited the fundamental theorem of calculus, which seems a little weird. I know y'all already know the fundamental theorem of calculus, of course, right? But I make this observation. You can think of the fundamental theorem of calculus as being a computation of an accumulating quantity, the accumulating quantity being change, and it's computed on the boundary. It's f of b minus f of a. It's you only look at the endpoints a and b when you compute that quantity called change, but just because you look at it on the boundary and you compute it on the boundary, does that mean that's where the change actually happens? No, that's obviously not true. Look, this is where the change happens. I can see the change happening. It's clearly happening for these points here in the domain. It's happening in the interior, right? And specifically, the derivative is the thing that tells you how much, right? So the derivative, the slope, is telling you rise over the run. Arguably, take the right point of view, the derivative is telling you change per unit size. It's telling you change density. It's telling you how much of this accumulating quantity, per unit size, of course, how much of this accumulating quantity is happening there. And we saw an example where we can explicitly and literally, right, use the derivative, interpret it as change density. Let's see here. So change density is the derivative. You can compute the derivative. You can plug in a couple of points that you might be interested in, like 1 and 2. You plug those in and just see what the results are. And it tells me right here with these numbers, clearly there's more change density, aka derivative. There's more change density at x equals 2 than there is at x equals 1. Which, of course, tracks with the obvious. Right? You look at the picture, well, of course it's changing. The slope, obviously. Right? So the point to this example is not that this computation tells us something we didn't already know. The point to this example is that it gives us an algebraic take that tracks with what we already knew. And this algebraic take is something that is analogous to what we're going to do in Chapter 7 now. I'm going to go back to here and say, okay, likewise, we've got this outward-oriented boundary flux. For example, there's a vector field and some surface that's a boundary of some solid, and certain amount of flux. Where's that flux coming from? Where in the interior is that coming from? And same deal. If you want to know where the flux is coming from, you look at flux density, namely divergence. And you take that flux density and you evaluate it at your 2 points that you're interested in comparing. And then you just see. If you want to know where there's more flux happening, well, this number is bigger than that number. So the flux density is bigger at B than it is at A. That means there's more flux happening at B because there's more flux density at B. Cool. Okay. All right. Okay, all right. So again, put it all together. Here's the theorem, and let's actually get our hands dirty now and do one. By the way, the way this tends to work is, and there are counterexamples to this, but most of the time it's going to be. Whoops, I wanted to be in the highlighter mode. Sorry. Most of the time, there's going to be some flux that you're going to want to compute, and you're going to do so by turning it into a triple integral of divergence. And what you're actually going to crank on is that triple integral of divergence. Okay, so here we go. I'm going to compute a flux. We have a surface given, and we have a integrand, a vector field given. We want to compute that flux. Fine. How are we going to do this? Let's take a quick moment to recognize what a nightmare this would be if we did this the old-fashioned way, right? If we plug and chugged, right? It's going to be a nightmare. Look at our surface. It's a sphere. How do we parameterize a sphere? Sines and cosines, spherical coordinates. Sines and cosines everywhere. X, Y, and Z, full of sines and cosines. That means that this formula for our vector field is a horror story of trig, right? You don't probably want to do that calculation. It's going to be really, really hard. Okay, so instead, we're going to look at our new theorem. Our new theorem says, hey, if you want to compute a flux, you can do so by instead computing a triple integral of divergence over that interior solid. Does that make sense? Okay. Now there's a catch. It's a important catch. Very importantly, this theorem does not say, let me come back up here real quick. This theorem does not say whatever flux you have, any sort of flux, you can compute with a triple integral. That's not what this says. The very, very important asterisk is this says boundary flux. This only works if you're talking about a boundary flux. Now, this is not some minor little asterisk. This is not some, formality, uptight mathematician kind of a thing. It really only works for boundaries. In fact, if you look back at the argument, why is flux an accumulating quantity in the first place? Go back to the picture we drew. It had to be boundaries to ensure that cancellation would happen. It just only works for boundaries. And if that's not persuasive to you, I'll make the further observation. It's got to be a boundary of something, because that something is going to be the domain for our new triple integral. If your flux isn't through a boundary of something, then there is no something to even talk about a triple integral over. It's not that this triple integral doesn't compute what you want. It's that there is no triple integral. Right? So, super, super important point here. Yeah, question?
What else could you compute flux over?
Just you can compute flux over any surface, right? You give me a surface, look back to chapter 3. We computed flux through a little flat piece of a plane, right? And it wasn't a boundary, right? But you can still talk about the fluid flow through it. So considering boundaries specifically does open up a lot of it's a very different sort of special case that we're considering. Yeah. Does that make sense?
Well, I thought a plane was a boundary, though. It's just a two-dimensional.
So one way to think of a boundary is that it is you can enclose. Let's see how to say this in 3 dimensions. A boundary is a surface that will contain birds.
Okay.
Right. So if let's take a sphere for example. A sphere. If I put a bird in the sphere, I got that bird. It cannot fly away. Right. If I have a plane, part of a plane. Does that enclose the bird? Nah, the bird flies off. Right? Does that make sense?
Yeah.
Right. Okay, so super important. It's got to be a boundary. Remember as well, also super important, the word boundary is a finicky word. It's a loaded word. It means oriented according to certain conventions. Arbitrary but standard. Got to follow the conventions. Okay, so that noted, let me go ahead and get into this mode. There we go. Let's look at our surface and ask, is our surface a boundary? And unfortunately, it's not. This surface, the inward-oriented unit sphere, that's not a boundary. It's close. Other than the orientation, it's all good, but the orientation matters, and this is not the convention for what the word boundary means. So, no. Bad news. That said, the inward-oriented unit sphere differs from the outward-oriented unit sphere only by orientation, and so therefore the inward flux that we're interested in and the outward flux that is a boundary and therefore that we can apply powerful theorems to, those just differ by a minus sign. Everybody good? You may recall we made an argument very analogous to this, our very first example when we were talking about Green's theorem. Right? You got to be really careful with the orientations. So all good though, because this now that we've accounted for the orientation with the minus sign, but this blue integral that literally is a boundary, and once you've got it written as a boundary, okay, well, boundary flux, oh yeah, boundary flux, triple integral of divergence, using the divergence theorem, boundary flux is triple integral of divergence, like so. Is that good? All right, be careful with that minus sign. By the way, and of course, don't forget to carry it along. So just full disclosure, I want to prep you all for exams in this class and, final, etc. The orientation's a big deal. The orientation matters because it's a significant idea, right? This is not, sign error along the lines of, we all make little 8th grade algebra level sign errors. Those are trivialities. Happens to the best of us, of course. That's not what this is, right? Orientation is a sophisticated, significant idea from the course, and it's graded appropriately to that point, right? So it's a big deal. You got to think it through. You cannot just, it's a minus sign, I'm not going to worry about it, and, blow it off and assume you're going to lose 1 point. On a 20-point question, matters of orientation, 4 to 5 points on a 20-point question. So it's a big deal, right? So please take it correspondingly seriously. All right. So it's almost all over at this point. A couple little details to talk about. We do have to compute the divergence. The divergence ends up being really easy. Keep in mind the divergence is the x partial of the first coordinate plus the y partial of the second coordinate plus the z partial of the third coordinate, which of course is 0. So divergence works out super convenient. It's just 3 plus x. So you could compute this triple integral by, pick your favorite. I mean, we're over the unit ball, so probably spherical coordinates be a pretty good choice. It's doable, pretty doable, no problem. Feel free to do it that way. But I do like to point out awesome little tricks when they arise. And by the way, this is another big one. When you have an integral that has two terms, you can correspondingly break that up into a sum of two separate integrals. Now, of course you can. Y'all have been doing stuff like that since Calc 1 classes, right? The big payoff here, though, is that while this integrand is not constant, it's not symmetric, it's not nice in any particular way, when you break it up into pieces, both of these pieces are nice. This one, because it's a constant, sweet, factors out, volume argument, right? High school geometry, super easy. And this one, because it's odd symmetric. And so you can make an odd symmetry argument, this integral 0 by symmetry. So it wouldn't have been that bad to do it by spherical coordinates, but it's way better to make this little observation. Right? So heads up, be on the lookout for this kind of thing. By the way, y'all have heard me point out many times how awesome symmetry arguments are. Right? I love symmetry arguments. Notice we didn't even have the opportunity to even entertain a symmetry argument for the original integral. And this is a common story. This happens a lot. And I'm pretty sure it'll happen a lot for y'all as well. That you got to break it up into separate integrals first. And then opportunities will start showing up like we see here. So it's a very important trick. It's not of much mathematical sophistication here. It's not like it's a deep point, but from a practical rubber meets the road standpoint, very useful little observation there. Okay, let's see here. We've got a little bit of time to talk about a physical example. This is my new, I'll say my recent favorite physical example for the three-dimensional divergence theorem. It's about light bulbs. I like it because it's relatable. Everybody understands light bulbs. Everybody's got pretty good intuition for, a light bulb sits there and generates photons and starts spitting out photons in every possible direction, right? And that generates kind of a flow of photons, which you could think of as being a fluid. It's kind of like a fluid, except instead of being a fluid of molecules, it's a fluid of a different kind of a particle, right? Okay. So this is an inverse square radial vector field. Now, an important little detail to throw out on this, not because the velocity decreases, right? You see how the magnitude of this vector field decreases as you go further out. Do the photons slow down? Of course not. Right? Photons, speed of light, right? That's pretty much constant. The reason that the magnitude gets lower as you go farther away is because this vector field does not represent velocity. It represents velocity times density. And as you get farther away from the center, right, the photons spread out. They get farther apart from each other. The photon density decreases. And so the velocity doesn't decrease, but the density does, and so the vector field magnitude decreases. Let's see here. Let me just say one other quick thing. Let's see here. I will... Oh, gosh. How much time do we have here? Is this seconds? Yeah, okay, we're out of time. I will pick up here on Monday. Y'all have a good weekend. See you later. Don't forget about attendance if I didn't already get you.